Okay, now I've sort of carefully constructed a couple of graphs. They're not perfect, but they are constructed fairly carefully, showing a power function with a y factor of 2.5, and I'll call that function f of x, and a function that I call g of x, a power function with a y factor of 6. So, we want to look at slopes of these graphs. And the first thing I'm going to look at is just the slope between the points, between the pairs of points I used to construct these graphs. So, okay, I can sketch a line segment between the first and second points of this graph. It's got some slope. I can sketch a line segment between the next 2 points, and I can sketch a line segment between the last 2 points. Then I can sketch similar line segments for the other 2 graphs, or for the other graph, for the pairs of points on the factor 6 graph. So, okay, here we've sort of got them. Okay, those aren't perfect, they aren't great, but they're going to have to serve the purpose. Now, I've pretty carefully marked off a scale for the x and the y axis. I haven't put numbers on the scale. I haven't put any numbers I want on the scale. But I have marked off the scale. Now, the other thing I'm going to do, for each of these segments, I'm going to attempt to locate the point at which the, let me see if this thing reaches. Not quite. Well, okay. I'm going to use this thing. This thing happens to have a scale too, but we're going to kind of ignore it. At what point does the slope of this segment, for example, match the slope of a tangent line to the curving graph? Now, by the slope of the tangent line, I mean we can keep this ruler parallel to this segment until it first touches the line. And that's going to occur at about this point. And just to keep myself honest, I'll draw a green segment to indicate that tangent line. Okay? Now, I'm assuming we know what a tangent line is. Okay, here. Where does the ruler first touch the graph when it's parallel to this segment? And I'm thinking it's going to be right about here. Okay? Now, what I want to do is I want to mark the coordinate where that occurs. Okay, there's where the tangent line becomes parallel to this one. Here's where the tangent line becomes parallel to the line between these points, to the secant line. And it also occurs somewhere between here, and probably about here. Now, I'm kind of fudging that, but there are the 3 points at which the slopes appear to, the slopes of the tangent lines appear to be equal to the slopes of the blue segments that I've sketched. Okay, so now I'm going to do the same thing over here, and get something like this, and I conjecture that this point, and really I should be using a different color. So I'm going to do that, but it's going to be a little messy here. I think it'll work out, and I think that occurs about here. I think this slope becomes equal to that of the curve about here. And I could draw that tangent line. I'm going to actually draw kind of a short one so it doesn't interfere with this one. And then on this last segment, I'm seeing that we have a little hard to eyeball parallel here, but I see something like this, and that appears to occur about here. Okay, and this appeared to occur at about the same point this one did, the purple and the green, and these two aren't too far apart, and they're pretty unreliable. Okay, now the other thing I'll notice is that in every case, the line from the origin to this point falls below this point. Now the line from this point to this point pretty clearly falls below this point. And this tells me, if you think about it, that the slope is increasing. And it's very clear that the slope on this white graph is increasing. It's getting a little difficult to see the slopes, of course. Now, I want to estimate these slopes. Okay, and I am going to assume that I've got just units 1, 2, 3, 4, 5, 6, 7, 8 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. Now I want to get the slope of each tangent line. Okay, so what I can do is I can do one of two things. I can say, okay, let's see. I can estimate the coordinates of 2 points on each tangent line, and I want the points to be as far apart as possible, so I could estimate these 2 coordinates, and I could estimate these coordinates. So I'm going to say that this tangent line, this green tangent line right here, has a slope of approximately what? Well, to get the slope of the tangent line, I'm going to want to use a different color here. Color I haven't used, and let's use red. Okay. Slope of the tangent line, as you should know, is rise divided by run. The rise is this side of the triangle, the run is this side. This looks like about 5.3, this looks like about 7.1. So I'm going to say that the run from here to here is about 1.8, and the rise from here to here, well, we're going from about 3 to about 6.3, so I'm going to say the rise is 3.3. So the slope of this green tangent line is what? 3.3 over 1.8, and that's approximately equal to a little less than 2, approximately equal to 1.8. Now I could calculate the slopes of all the rest of the tangent lines, and I have a choice in each case of actually calculating the slope of the tangent line or the slope of the blue line that's supposed to be parallel to it. If I look at the green line here in the line to which it's supposed to be parallel, I don't think I did a very good job of getting it parallel, but you can kind of use your judgment. So you can either calculate the slope of the tangent line that I actually drew, or the slope of the line between the pair of points that I used to get the tangent line. In other words, the slope of this blue line, the slope of this blue line, and so forth. So what I'm asking you to do is find the slope of each blue line, or if you prefer, of each of the tangent lines that I sketched.